by laying out the goal of the research. The goal of the research is to generalize right. By recalling what is the classical Thomason's homotopy, Now, this is the category of content from D. D is a small category. So this is the category of functors from D into cat. Then we have the category of simplicial sets. In here again, I'd like to see category. Now, there's a functor from here to here, which takes F. F, right? So F is a functor from D to cat, and the nerve gives you a functor to simplicial sets. Now, there's a functor from, in the other direction, which takes a functor F into the classifying space of the Grothendieck, construction. Okay.
Very fast.
Yes.
I know what the nerve of the category is. It's I don't know what the nerve of a functor is.
Well,
You're
that's
taking the nerve of a functor F.
That's what I was describing. This is just composition. This is the function F.
Okay, so
You just compose it pointwise.
So you get a functor to the category of simplicial sets from the diagram of simplicial sets and will take its coordinate.
okay.
Homotopy
I see.
coordinate. Yeah. Because not the nerve of a functor is just a composition of two functors.
Well, the Thomasons, the classical Thomasons, this states that the geometric realization is equivalent to the construction, and this this is actually a homotopy equivalence of topological spaces.
Which should be the realization of the right hand side.
Well, B, you can think of landing in topological spaces. Oh, okay. Well, I mean, when you're saying classifying spaces, well. Okay. We could do that. Yeah, sure. Well, the reason that this is important here is that it's not necessary that this is always fiber. Okay, that's why we're taking the geometric realization. So that's all. But this is always fiber. Okay. That's the classical Thomason's theorem. Now,
What is the difference? So is, I didn't hear what Sasha was saying, is B then
the classifying space.
like the geometric realization of the nerve, or what would you, or simply the nerve?
Well, it's the geometric realization yes, you could say that it's the geometric realization of the nerve of this.
Yeah, what is your definition? I mean, I might say it, but what do you mean by it?
What do I mean by that?
Yes, what do you mean by that? You said I could say that, but what for you is the definition?
Okay, let's just say that I'm doing a fibrant replacement in the motor category. Okay, of the nerve.
Okay. Thank you.
Okay, so this is an equivalence, a homotopy equivalence in topological spaces. Now, we have this category here. It'll be good to recall the definition of this Luther construction. Now, the objects of F is the same. This would be, this is the set of pairs. And the morphisms here. This could be, these are best defined by the following diagram. Well, let's say, let me try to describe the morphism from Bx. Into let's say Y. So this is a pair F and H. So F is a map in D from D to B1. And H here is a map that goes from and this is a map in, let's see. Okay. So diagrammatically, I can define this thing as X, and here is the arrow H, Y. This goes here in F of F, and I can think of this circle as a space or the category F of D. And we can draw another circle here. That's a model.
Amit, for the record, instead of in parentheses, there should be, you meant to be F instead of the bar. I guess this was F maps to, in parentheses for the Grothendieck function, B to the right. Yeah. In parentheses.
Yeah.
When F changes, you meant the bar, but F doesn't change there. Right? Yeah, great.
Right.
Yeah.
Okay, so this is a little recollection of the classical Thomason's theorem. This was done sometime in the 80s. Okay. Now, a few years back, this theorem was, generalized to spaces by Hoyts and Mordaunt. Let me explain that. So this is an analog. Yeah. Oh, hold on. Let me fix some notation here. Now, SP here, I would SP, I would mean the model category of simple sets with a Kahn model category structure. That means the fibrant objects in this are complexes. Now, this is my choice of the homotopy theory of spaces, but this theory would work for any choice of spaces. Now we have a similar diagram here also. Now D again is a small category, so we have the category of functors from D into simplicial sets. Then we have the over category of simplicial sets. Over and then would be. And here again, another same. Now, in 2009, Jacob Lurie gave two functors. Now, in these diagrams, the left adjoint would be on top and the right adjoint is on the bottom. Okay. This is our lower shred. This is kind of a rectification functor. And here we have this functor we are calling Lurie's broken. Now, I'd like to put some model category structures on these, category. This has the projective model category structure. We are in spaces, so this, this here is really this model category. Okay. Simplicial sets. Maybe I should change, I intended to write SP there, but maybe I should change this. SP is this model category of complexes. Now, Lurie showed that this is equivalent equivalence. This is the right equivalent functor, and this is the left equivalent functor. Now, I told you that this has the projective model category structure. This category here is what's called the covariant. This structure is by Joel. If I'm not mistaken, then this was in 2007. That's when it was put down. Now, the covariant model category structure, the fibrant objects are what are called left fibrations. Now, I don't want to get into a rigorous definition of a left fibration, but conceptually, a left fibration is a map of simplicial sets. Okay. Such that the fibers, right, the fibers of this map would glue together into a map of simplicial sets between S and Khan, where this Khan is the quasi category of Khan complexes. So to be more precise, if I have a vertex S in S, then this functor would take S to the fiber. So if you have an edge in S1, right, then E would go to a map from source. This is the model category used, fibrant objects, left fibrations. So this was done by Jacob Lurie in 2009. Now in 2014, 2014, Hoyts and Mosaic wrote functors in the opposite direction. This functor is denoted H lower shred, and this is H upper star. Right, John? That's your left adjoint. So you can see that the functors are going in the opposite direction. Now here, the right adjoint goes from here to here. Here, the right adjoint is going into, it's in the opposite direction. Right? So this is what, Hertz and Mordek, defined. And then they go on to show that, this is a equivalent adjunction between the same two, model categories, and this is also equivalence. Right. Now, as you can see that I have four, functors here. I'd like to give a definition of these as to what exactly are these functors. Maybe I should raise this. This. F, F is a functor here. Within the homotopy component. And I'm talking about the when I say homotopy element, I'm talking about the standard construction of the homotopy element, which means this is the diagonal. Part construction. Now, the right adjoint here. This is a functor from D into spaces. Now, its value on an object D is defined as the harm.
Object D is probably the vertex of the corresponding spatial set.
That's correct. Yeah. Well, it's a vertex of this.
Correct.
No, yeah. This is the under category. This has the obvious, target map that goes into the node of B. Right? The maps from here, X and here. And these maps are in spaces. Not in space. Okay, I have these two functors. Now, the rectification function or lodestar or lowest rec. This is now finally the most important functor, which is this, the Lewis growth and deconstruction functor. Let me try to explain. Probably the best way of doing this is that you can explain this in this a certain diagram. I can't use that platform, right?
Probably not.
Okay. Maybe I can use this one.
This one.
Yeah.
To people up there, down there, you can see it.
So I'm trying to explain what is. So the data synthesis here. Okay. One synthesis. Well, really, these are the same as that in the ordinary This is actually a pair. Sigma. One, so that means sigma is a map. Or something like these are the- Zero. V1. So here I have an object x0. Yeah. Now I transport this f of f into f of v1, and then I pick up an edge. So this what I have described here. This is a map between v0, x0 to these are one surfaces. Now, okay, I don't want to erase this. Let me go here.
Sorry. What is lowercase of your?
Oh, sorry.
Oh, it's
Well, the two sequences. This would be sigma in two symbols in the nerve, which can be, B0, B2, and B2. Yep. Right. And now we have B0. Have a zero simplex here, x0. Then I have one simplex here called x1. And then in f of d2, I have a two simplex here, which we call x2. Now, as in the case of one morphisms, this is transported to this. Okay, F1. Right? Now, this arrow or this edge is going to be, transported here. Yeah. So, in other words, you could write this as sigma x0, x1, x2. This is a two simplex, right? Such that B2 x2 is x1 sigma is what I described here, and B1 x1. Well, I'd like to remark this is far, far away from Rudy's description. Because, this one. Construction company. Now he has defined it quite abstractly, and it's not obvious to extract this out of it. Okay, so now I have all these, functors here. I've described all these functors. Now let me describe what is the Thomason's theorem. Equivalences. These together imply the zigzag. Of P to 200. Good. Okay. This is again a function here. So in other words, even in spaces, Newton's Copernican construction, right, picks up at least the homotopy type of the homotopy function. Okay, now let me get to what we have done. Third part of the talk, I would describe Thomason's theory or market. Now, for that to make sense, I would have to explain what are marked quasi-categories. Now, there is this model category of spaces, SP, spatial sets, with the Kahn model category structure on it, and the fibered objects or Kahn complexes here. Then there is a model category of quasi-categories, or which is also called the Gerard model category structure. On simplicial sets, the fibered objects here are quasi-categories. Okay. However, there are a few drawbacks of this, category. First of all, this is not a simplicial, model category. It is a Cartesian closed model category, which means it's enriched over itself, but it's not simplicial. That is one drawback. The other drawback of this category is that the homotopy colimit, this is very, very far away from the homotopy colimit of F taken in this model category. Yeah. This thing is a homotopy colimit here, but it's very far away. So a lot of modifications have to be done to this in order to make that a homotopy colimit here. So, there's another model category, which is noted this way, wherein this is very close to homotopy. Okay. Moreover, this is a simplicial model category. So because of these two things, we would first develop a theory in this category, right? And then somehow push forward that theory into quasi-category. Now, I'd also like to remark that both these models or whereas this is a model form spaces. Now, I need to describe a similar diagram in case of marked simplicial sets. Maybe I can modify this diagram also. Okay. over the nerve of, D. Now, if we are talking about an over category in marked simplicial sets, then the base should also be a marked simplicial set, right? So we, we turn this into a marked simplicial set by marking all the edges. We mark all of the edges. Yep. Well, the same thing happens here. Now, we keep the functors the same. Now, these are the same functors, right? Same four functors, the base functors are the same, but we just modify them, so that these are now functors between, this, category of marked simplicial sets and this over category of marked simplicial sets. So I'll put a plus here, I'll put a plus here, and a plus here, and I'll put a plus here.
Wait, I want to tell us what a marked simplicial set is.
Oh, yes, I'm sorry. Thanks for, thanks for.
You started
reminding me that.
talking
Yes.
about this as if we already know what it is.
Yes. Hold on. Let me Mark. By edges, I mean one surface.
You have to choose a simplicial set.
Now, these are objects of this category. Simplicial sets plus. Now, morphisms in this category are those morphisms of simplicial sets which preserve
Marking.
the markings. Mark edges.
Quasi categories plus it also needs to be explained.
Yes. Yes.
The vibrant objects in this model structure.
Okay, there is the obvious forgetful function. I think before we get to this. The model category structure here is actually lifted off of the model category structure here. Yeah. Now, the vibrant objects, let me, describe what, the vibrant objects there are. So, this, right, is a pair x epsilon, right? X is a quasi category, right? And epsilon is a pair of equivalences. X. Now, an equivalence in a quasi category is an edge that turns into an isomorphism in the homotopy category of X. Okay. These are vibrant objects in this. Now, there's an obvious forgetful functor from this model category in this simplicial sets. Theta, right, which forgets the marking. This is a Quillen equivalence. This is the right Quillen functor of a Quillen equivalence between these two. I think now it's clear what these are. Well, now let me explain what these pluses here mean. Maybe I should start with the rectification function. So. This is just next. Every edge of this is marked and every edge of this is marked.
The sharp means every edge is proper.
So it's exactly, the, base function is just this. Those are the markings. Okay. Now let me explain what else. What's the plus?
Where's the little d on the left hand side? It should be a d in parentheses on the left hand side. There should be a little d on the left hand side. It's missing one.
Value of D.
Yeah. It's missing one of the equations over there as well.
Sure.
That's okay.
Let me explain what is this. Okay, this thing, this plus. Now. The plus here means that. Well, in order to explain this thing here, I'll have to tell you that this is, there's a functor from here and from that, right? Now, if we recall the one simplices that we had for the growth of the construction functor, right? There was a projection into the nerve, right? So just that, if we recall that the n simplices or something like this. So the projection of that into the nerve would give you a functor, or would give you a simulation marker. Now, this is always what's called a co-Cartesian fibration. Now, a co-Cartesian fibration, conceptually means that this simplicial map should determine a map of marked simplicial set on the nerve of P. I shouldn't say one simplicial set, but it should, determine a simplicial map from the nerve of D. Plus. Now, Q cat plus, this is the quasi category of. And this is the same, thing. So if I have D0, there's a vertex here. X D0 and an edge. This is an edge here. Should give you a map from X source. The only difference is that these are now marked simplicial sets.
What's X?
Okay, now in this case, okay, now these are co-Cartesian fibrations. Every co-Cartesian fibrations, the total space of the co-Cartesian fibration, right? These has certain edges, which are called co-partition edges. Edges which have a certain universal property. Right? On that. Now, I give you an example. If you know what are horizontal arrows in the construction, then those are co-partition. So I think it's enough to the actual definition of this thing is quite involved, but these edges have a certain universal property on them. So I want to mark these edges. Okay, so these are my marked edges, just the co-partition edges are marked. Now, similarly, in this functor, the base functor is the same as in spaces. Now, again, I end up marking co-partition edges here. Now, due to the lack of time, I'll just leave this, by saying that there's a, this also has certain markings, but that doesn't play much a role in what I'm going to display next. Now, I think I should state some of the main results here. Here's the first thing. Function. B. And then I have the forgetful function that goes to this, which just forgets the base. This is this composite. This is our first result. And this is a function. Now, if I remove these pluses, right, and just consider the Joule model category structure, this is not going to be okay. Now, here's the second result. The left derived function. And right. Right. Okay. Adjoint. On the homotopy category of and the homotopy category, like the over category.
They seem to go in the same direction. Right.
No. Yeah. This is going in this direction. This is going in
The same direction. Which is the same from.
well. Of course, they are, between the same two categories.
Yeah.
But the direction, when I say the direction reverses means that this is the right adjoint. And this is the left hand. Okay, that is the difference.
I don't think.
Oh,
So they don't form in the.
no, hold on. What I meant was, no, I don't mean this. Yeah, thank you. Thanks. I didn't mean that. What I meant was this. This. Yeah. Yes. These two. This is the,
So then it should be the right.
yes, this is the right function. That is correct.
Maybe you meant to say something else about the previous factors.
No, this is correct. This is the right. The right function. This, right? And, and also the right function is this. Yeah. That they are adjoint. Equivalence. Between these two. Now, if the right, this means this is an equivalence on the homotopy categories. We know that these are equivalent pairs. Show that these are equivalent pairs, right? So this is. Yeah, so that's our next, that's a corollary to this result. Let me write down the corollary to this. So here's corollary one. So it says that the equivalent pair. Is it equivalence? The second corollary. Yes. Now, this follows from this theorem, right? But this has been proved in 2009 by Lowry and Amit. Right? So our theorem gives another proof of these. Yeah. Third corollary 3 is that without the modules. Let me give you another example. Now, a key step in the proof of this theorem is that we, construct a map. You call it ID within the natural, weak components between. And ID plus. Both these are natural, weak equivalences.
So this is
So-
actually the analog of Thomason's.
This is the higher categorical or the analog for Thomason's theorem for marked quasi-categories. Okay.
And also for quasi-cases.
No, this is, this one is for spaces actually. This is for spaces.
Spaces.
Yeah.
Let's see.
Okay.
I thought it was, okay.
Okay, it's showing, no, this is for spaces. I still have to address the quasi category, that's the fourth part. of the talk. Thomason theorem. Now, I've already discussed that there's a forgetful functor from marked simplicial sets into quasi categories, or into simplicial sets. There, there's another pair of functors. Quasi category. Yeah. This way, functor E would take a simplicial set here and mark the equivalences. Okay. And this side, functor L, would localize the marked edges, basically invert all the marked edges. This gives you an equivalence on the homotopy theorems of these two, or on the homotopy categories of these two model categories. Yeah. So the last thing is that in Thomason's theorem for quadrant. Says that L this is a natural weak equivalence, and basically what we are doing is that we take the classical homotopy coelement functor and then invert the co-Cartesian the arrows, and that gives us a homotopy coelement in the category of quasi category. That's what this is.
Very good. Let's take, it's a very interesting talk. Questions?
What's the key technical difference between more quanti-categories and quanti-categories that might prevent you from working with quanti-category directly from the start?
Well, of course, one thing is that in marked quasi categories, this is directly a homotopy coelement, just by marking some edges. Right? Here, on the other hand, now we have realized that I have to invert edges, right? In the case of quasi category. The other main difference is that marked quasi categories, the model category of marked quasi categories, that's a simplicial model category. Right? So that there are advantages now. In a simplicial,
Unlike the category without models.
exactly. Unlike the Joel model category. Now, in a simplicial model category, there are, there's a very good recipe of computing homotopy columns. Right? That's unavailable in yes.
So is there like so does this automatically, because you got a coelement, does this automatically relativize? Like, does this give you some kind of homotopy coelement functor for like the cohesion model structure on simple marks and sets over some base.
Basically, what you're saying is that we talk about the over some, right? These functions, and then what you're saying, or what you're asking me is that either this or this, a modification of that would give you a model category a homotopy, co-limit functor on this. Well, that's a good question, and I don't have an answer to that.
Yeah, the question was whether it was automatic. So probably it's not.
I don't think, well. My suspicion is that you should be able to get one, right? But if, if you ask me, why is that true, or, how to prove that, I have no idea.
Other questions? I have one, just clarification. So corollaries 3 and 4 actually also take place in the category of spaces. And so this is basically, they were known because of Poisson Nordhae's theorem, but you are given a new proof of their results.
Yes, yeah.
Okay. Other question?
If I have a minute, then I would like to say that this has the reason for doing this. This is actually some intermediate research. I'd like to point this thing out. This is related to the theory of symmetric monoidal infinity one categories. Okay. Now we have two models for symmetric monoidal infinity one categories. One is based on gamma sets, right? And then one is based on co-Cartesian fibrations, the model structure, co-simulation sets, plus over whatever. Like, well, actually, it's in this case, it's the nerve of gamma up. There are two structures, two models for symmetric monoidal infinity one category. Now there's equivalent between these. Yeah, there is one. However, if you look at algebras over the Baraticals operators, right? Into Baraticals operators, then it's not known, or well, it is generally accepted that there is an equivalence, but we want to write that down, that equivalence. Yeah. And it turns out that the functor that goes in this direction is a homotopy co-limit functor plus a little bit more. So having a good understanding of the homotopy co-limit functor is, the immediate aim of this research is to prove this theorem that there is a direct equivalence, equivalent equivalence between these.
Other questions? If not, let's thank Amit for the very interesting talk again. We'll be taking off to the airport while some of us can have beer. I don't know.
I mean, it doesn't look like. Did you have any interest? No, okay, yeah, it's we got.
Yeah.
End of semester.
I have an interest starting from next week, but I will be gone. Out of town for the rest of the semester. I will be joining you virtually.